And our last speaker for this session is Dino Bechtesevich. It's also a recorded talk. I believe Dino will be able to answer questions on the Discord platform. And the title is Lessons Learned by Adding, sorry, I can't read my own handwriting. By adding cloud support to Rubin software. There we go.
Hello, everyone, and thanks for coming to my talk. My name is Dino Bechtesevich. I'm from University of Washington, Seattle, and I'm working with Andrew Connolly and the Rubin data management and adding support to Amazon Web Services to Rubin software. Next 12 minutes, I'm hoping to go quickly over the project, the way we did it, and talk a bit about the lessons I learned doing it. Rubin Observatory is an 8-meter telescope currently under construction in Chile, on which the legacy survey was based in time, while this LSSD sky survey will be conducted on. The 10-year sky survey will image the entire southern hemisphere every 3 nights, producing about 20 terabytes of data nightly. The end-delivered data volume is estimated to be between 300 and 500 petabytes. This data volume is kind of new to astronomy, so a lot of discussion and planning is happening regarding what data reduction pipelines need to look like and how will the users be given access to this data. The project itself would reduce the data in 3 locations, UK, France, and the US data facilities. Alongside processing the data, they would provide long-term storage and would provide data access to the end users. This would be achieved through the LSSD Science platform. The Science platform was designed as a set of services facilitating data access via portals, APIs, explored the Jupyter Lab notebooks. To provide these services and resources for them, 10% of Rubin compute resources are designated as shared user compute resources. The collaborative Jupyter Lab work environment that enables in-depth next-to-data analysis based around this idea of bringing analysis to the data instead of the other way around is what really caught our eye at UW. We began wondering if, instead of relying on the 10% allocated shared resources, could we also bring our own compute resources to the data? How useful would this be in enabling and or accelerating science, and how costly would it be to do something like this? The obvious implication here is that we don't want to purchase long-term standing hardware. We want to utilize cloud resources to achieve these goals to reduce costs. Cost comparisons between cloud and on-premise solutions are very difficult, but as a pure exercise in estimation, we can take 1 year Rubin on-premise deployment cost estimates and then compare them with the AWS calculator estimates. And we can see that while they're not very different, they do lean ever so slightly towards the cloud deployment. Unfortunately, the general consensus seems to be that in the long term, storage of large amounts of data in high availability data storage services is what drives the cost of cloud deployments. And there's no clear and easy way to estimate with certainty the point at which on-premise deployments would outperform cloud deployments in cost. But given the simple estimates above, and the fact that, let's say, if the 24 instances were procured all upfront standard reserved instances instead of on demand, the total estimate would stand at 285,000 United States dollars, right? The prospect starts to look quite attractive. We felt optimistic enough to move forward and add cloud support to Rubin Science pipelines to see if we can improve on this simple cost estimate. The slide I'm showing a schematic representation of Rubin middleware component that ties the science pipelines being more on the right-hand side to the data I/O abstraction, the data butler on the left, right? The data butler is the abstraction that interfaces all data access and formats in Rubin middleware, making the science algorithms file system and file format agnostic. The butler does this by keeping tabs of the data types and locations in a database called a registry. And then when asked, it retrieves them from the data store. At the time of the development, this was just the POSIX file system. Right? The algorithms that are encapsulated in tasks can be chained into pipelines that are represented by directed acyclic graph, which makes this design able to execute very complicated workflows. To adapt the code to cloud services, we implemented S3 object storage functionality for the data store, and we added a PostgreSQL backend for the registry. At the time, they used SQLite for the development of the middleware component, and we wanted to use the AWS relational database service to launch servers in AWS, so Postgres was a requirement for us. There's not a whole lot to say about the development experience here, except that it can be frustrating at times because of the sheer amount of services offered by AWS and the confusing ways in which they interact with each other. I would still say that the majority of the core functionality was implemented relatively fast. This development wasn't a horrible experience. It's definitely personal opinion and not a general fact of the matter, because this was definitely helped along by the design choices made in middleware and the experience with AWS resources I had from previous similar projects that weren't as successful. Just keep that in mind, that there's an associated learning curve for each cloud provider. Had to pick a pet peeve, I would definitely pick how confusing the tooling can be. There's the management console, the CLI tools, which have two different versions now, the V1, installable by Conda, pip, and system package managers, and then the V2, the newer one, which has to be downloaded from a URL and seemingly contains an embedded copy of Python in the installer. The Boto 3 Python SDK is pretty great, but it has no official testing libraries. We use Moto, and that was a pretty pleasant experience, but it's important to note that Moto doesn't cover all of the AWS services to 100%. Boto 3 itself can be a bit confusing since similar functionality doesn't always do similar things like the example on the slide, so keep that in mind. Another thing to keep in mind is that S3 is not POSIX compliant file system. It will try to look like one though. Empty keys will be displayed and act like directories, but in reality, the mental model you want to adopt is more like a flat list of keys. Right, so searching for matches has to search the whole list, but we don't have to do that, which can save on cost and performance. Little details like this can matter because, for example, if you scan that 20 terabyte data store just once a month, you'd pay about $10. But if this happens constantly in your code on 1,000 worker nodes, the end bill could measure in hundreds of dollars. And not to mention that this is costing in performance as well. Most of this, though, is not like an insurmountable problem, just kind of the reality of working with these systems. The end product, though, is the ability to run processing from any compute resource with the data persisted somewhere non-local, like S3 buckets. And since the AWS proof of concept was completed, the data management team added interfaces for Google Cloud Storage and WebDAV as well. What is missing from this picture is a way to scale up, some kind of a batching system and some kind of a resource procurement system. In our project, these roles were fulfilled in tandem by Pegasus Workflow Management System and HD Condor. To use Pegasus, we have to take the created science pipeline stack and then convert it to an abstract workflow, which is additional step, but this gives us more flexibility to adjust different parameters like CPU and memory requirements, clustering, staging, etc. right during this planning stage. The end product is an executable workflow, which is kind of just like a set of scripts that can be executed through HD Condor, like a regular scheduler. HD Condor also gives us HD Condor Annex, an additional tooling on top of HD Condor that provides the ability to provision compute instances with specified configuration and from specified Amazon Machine Images, AMIs. These instances can be dynamically added and removed from the compute pool, for example, when they idle for too long, which saves a lot of money. So in overview, this is kind of what the build system looks like. User would acquire a head node in which they would log in, and they would create a science pipeline workflow bag, which they would convert to an abstract workflow and submit to Pegasus. And if they needed, they could procure more compute resources using Condor Annex. In this proof of work concept, we built a system in which the user has complete control of the stack, which is both good and bad. It's good because the user gets absolutely complete control of any part of the system, but at the same time, it's also necessary for them to learn the tools, and there is a lot of friction there. There is a lot left to be said about integrating Pegasus and HD Condor with Jupyter notebooks, unfortunately, because they were never really intended to be used that way. However, the newer versions of these packages made great advances, making that possible. It's also possible to script out a lot of initial system configuration and resource creation, like the registry and the buckets, via Terraform scripts or Packer scripts, for example. This requires a bit of extra work and is external to these tools, which onboards kind of more and more maintenance to the developer. And that's another thing we learned. As we continued trying to develop and support this project with real users and real processing requirements, maintenance became a lot of work for a small team of me. Constant battle, between shared package version mismatches of Pegasus and Rubin, change of development direction from CentOS, changes to Rubin build system and HD Condor functionality. With so many moving parts, many of which are active developed in this area, the automation scripts and the deployed infrastructure requires constant adjustments. A fair question also here to ask here is, who also gets charged for all these resources and how do you control the limits? AWS uses a very powerful user identification and authentication system, but it's also kind of leaky. It can limit access to users to some services, regions, or instance times, but for example, it cannot limit the maximum number of instances users are allowed to launch or the maximum volume of EBS drives that are attached to those instances. I'm not really sure even now what the proper solution would be, but perhaps a more reactive approach is one of the options. Monitoring CloudTrail and AWS config logs to delete the resources that cross the limit is a way to go, but that is also a lot of tooling. Different architectures can help us out here as well. If we do not allow users to complete control of the hardware resources, we can use HTConda UID domains to control the amount of resources as well as what resources users can access, which is great. But who is the person that controls and maintains the system then? And more to the point, these solutions seem to becoming more and more complicated. Perhaps answer already exists, we're just not aware of it. I believe data management teams are looking to Pandas Workflow Manager. Pandas is a tool of choice for the high energy physics community, which has been experimenting with cloud much longer, at least since 2017. So a lot of functionality could already be implemented. I want to point out that a lot of these solutions that discussed so far also don't really try to separate ourselves from the service provider specific tools like IAMs and AMIs, right? Containerization could be an answer to that problem because HTConda can launch containers as jobs, but the problem can also be that these containers become very large. Stack install is typically 10 to 15 gigabytes alone. And there are other issues as well. But overall, there's just still plenty of work and ideas to explore in this area. And probably the slide everybody wanted to see is cost estimates. The details of estimated costs and workflows used to estimate them are best explained in more detail in the reference paper at the bottom of the slide, because they come with error bars and caveats and definitely could benefit from more work. The basic gist is that we estimate total data release production runs to be order of 0.9 million United States dollars on premise for 1 year, and in $0.7 million in cloud. Of course, these do not account for new optimizations like caching and decentralizing registry access patterns implemented since then, which do bring the cost even further down. Egress and storage costs still remain substantially large for large data sets. I think one of the important lessons that we also learned here is that if you can do the same work in 1/10 of a time on 10 times as many resources, you won't have to pay more. You'll pay the same price because that's how costing scales in cloud. It doesn't matter if you get results in a day or in 10 days, it costs the same, which brings about a different philosophical question, and that's at what point does enabling and accelerating science, shareability of the data, and risk mitigation aspects of using cloud resources surpass the monetary cost of cloud? A bit of too optimistic future perspective here might be that there's still many things that could reduce their cost footprint in the cloud that could be implemented. Tier storage would allow us to amortize those costs. New services like Cloudflare Object Storage supposedly won't charge you great costs. Long-term standing contracts would be a good thing, right? So there's still plenty to explore there as well. In the interest of time, I won't repeat all the points made here, but in short, containerization is likely the way to go. More optimizations are possible. Extending the cloud deployment remains cost-effective if we can implement those. Rubin has recognized these facts, and they've tendered contract to Google Cloud to develop and deploy the intermediate data facility for the first 3 years of the LSSD project. If these are topics that you're interested in, I would definitely recommend paying closer attention to the Link Framework project, which is a collaboration between University of Washington, LSSD Corporation, and Carnegie Mellon University, as they will be attempting to solve exactly these issues. And they will be hiring soon, I hope. I think that's all I really have to say. Thanks for listening. Apologies for walls of texts. I can take questions now.
Thank you for that. There's one question that come into Discord. Could you comment on any specific lessons learned from DP0 as you have actual users trying out the platform? This is from Michelle.
Yeah, thanks for the question, Michelle. Unfortunately, I'm not, DP0 and the IDF facility is on the Rubin side. And I'm not personally involved in the deployment of the DP0 on IDF, so I would not know much about that. What I do know is that they would host notebooks and data, but I don't believe that there would be a batching system for large-scale processing involved in DP0 at the moment. I see you already gotten your answers in the chat there.
Thank you. I see there's also other answers coming in through Discord. Would anyone in the room like to ask a question? Okay, so it seems like the conversations will continue online. So I see that in your conclusions you mentioned that they'll be hiring soon. So I want to just highlight to everyone in the room and online that there's a job board channel associated with the Discord platform where any positions can be advertised. So thank you very much again for this great talk.